So just by way of introduction, a lot of the information that's coming from this webinar, or that's presented in the webinar, is coming from an article I wrote for Streaming Media Magazine that showed up right at the end of December, and it was the first article or comparison that I've seen that compared EVC, VVC, LCEVC, along with AV1, HEVC, and H.264. So I was pretty proud about that. Now, if you want to look at the command strings that I used for the results we'll be showing in this webinar, you can go to the article. Same deal with the description of the test clips and any other test procedures. You can download the RD curves and the BD rate stats in a separate document on the right, mentioned that a moment ago. And this presentation is more a summary of the results and kind of an overview of what's happened over the last 12 months than a description of what was going on in the article. And what I found in some of my predictions, some third-party predictions, not a real at the what happened in the review. And the presentation is probably going to run a bit long. Someday I'll have a presentation that's got fewer slides than minutes, but this unfortunately is not one of them. So this is the advanced codec overview. This is, when I think about what's going to help a codec succeed or allow it to succeed, these are all the factors that I took into play. And we'll look at this in an agenda in a moment. But if you take one slide away from the presentation, this is going to be this slide, and it kind of summarizes the findings of everything that we reviewed in the webinar. So we had the brief introduction. We're going to look at the quality and unique selling proposition. USB, got that wrong. Then we're going to see if the codec has a known royalty structure. Rich parents help with codecs and in life. We'll look at that. And then we'll look at producibility and playability, which really are two factors that obviously control how and when a codec can be deployed. So in terms of quality, we're going to look at what I found with streaming media. And then we're going to kind of correlate that with some tests that looked at some of the codecs performed by Moscow State University, which is one of the authorities on codec testing that I really trust and really respect. And then we'll look at some key takeaways on the quality side. Now, all of these results are presented in terms of relative codec efficiency as it compares to X.265 very slow. Now, just as a caution, we're going to be talking about a lot of different codecs here and a lot of different standards. And every codec within a standard, X.265 is an HEVC codec. It's going to perform differently than the MainConcept HEVC codec. And it's going to perform differently depending on which preset you use. And I go into why I chose the presets that I used for the testing in the article itself. But just keep in mind, I'm not saying HEVC is great or HEVC is awful. I'm saying this particular implementation performed this way. And it's the same thing with VVC. We looked at the Fraunhofer implementation. EVC, we looked at an open source implementation. HEVC, we looked at X.265 and the MainConcept. And for H.264, we looked at X.264. And AV1, we looked at the AV1 implementation in FFmpeg, lib AOM.AV1, something like that. It's detailed in the presentation. But these are the results that we see. I'm not going to go over them here. I'll go over them in a slide in a moment. And then these are similar tests performed by Moscow State. Now, Moscow State didn't look at LCEVC, and they didn't look at EVC, but they looked at HEVC, AV1, and VVC, multiple implementations of all of those codecs. So these are the common data points, again, all as compared to the X.265 codec. And I found that the Fraunhofer implementation of VVC was 43% more efficient than X.265. MSU found that the best VVC implementation wasn't Fraunhofer in their testing, was about 50% more efficient than X.265. Again, MSU didn't look at the EVC, but the best AV1 implementation I found was 38% more efficient than X.265. Moscow State was 39% more efficient. Again, it was a different codec, but these are, similarity in results. Moscow State didn't look at LCEVC. They looked at multiple other HEVC codecs besides X.265, and they found that the ones that they looked at that were most efficient were 26% more efficient than X.265. And I found that the MainConcept HEVC codec was 20% more efficient than X.265. EVC it didn't look at, and then X.264, I found that X.264 was about 51% less efficient than X.265, and MSU found it to be 35% less efficient than X.265. So the common takeaways you see, these are the ones that both streaming media and MSU looked at. We see VVC is between 43 and 50% more efficient than X.265, which is a pretty big number. AV1 is around 38% more efficient than X.265, another pretty big number. And other implementation differences, other HEVC implementations are up to 26% more efficient than X.265. And again, that X.265 is between 35 and 51% more efficient than X.264. Now, other takeaways that are streaming media only is that EVC main was very impressive. If you download the BD rate stats and the rate distortion curves, you'll see it was very close to VVC in a lot of the test clips that I looked at, as was AV1. I mean, the top three were very closely clustered together. LCEVC with X.265 as a base layer, which MSU didn't look at, was 22% more efficient than X.265 on a standalone basis. And then EVC baseline, which is supposedly the royalty-free implementation of EVC, was 45% more efficient than X.264. So it was behind HEVC, but its its target is H.264, and it proved to be much more efficient than X.264 in my tests. Now, a caveat here, all of these tests that we're discussing are BD rate stats, and BD rate stats are computed with 4 1080p files of different data rates and different quality levels, and you don't distribute video with 4 1080p files. You use an encoding ladder. So if you want to try and compute how these benefits will apply to you, you're going to have to look at a real encoding ladder, and you're going to have to look at real distribution statistics. Now, when I looked at LCEVC, I looked at it in 2021 for live use cases, and we looked at real encoding ladders, and we looked at real distribution statistics. And when I talk about encoding ladders, the sports ladder is shown on the right, and we compared X.264 with LCEVC with X.264 as a base layer. And we did not 4 1080p files, we did obviously the full encoding ladder, and we created a unique encoding ladder for LCEVC that was different than X.264, because if you were using LCEVC, you would use a different encoding ladder for that as you would for X.264. Now, so that's one aspect of it. And when I looked at H.264 compared to LCEVC with X.264 as a base layer, I found that LCEVC using BD rate stats was around 42% more efficient. If I just looked at the encoding ladder implementations, the full ladder advantage over H.264 was 32%. And I'm looking at the bottom left of the slide here. Now, once I took into account the estimated usage, which rungs were being actually viewed by the most viewers, that reduced the overall bandwidth savings to 22%. Now, it's a lower number, but it's a much more realistic number, and 22% is actually pretty good for implementing a new codec. It's just, we hear 50%, we hear 40%. If it's BD rate, you're not going to realize all that. Now, you have to look at your estimated usage, because if 100% of your distributions are in profile 1, you're going to get every bit of the codec savings that you get in the top rung. That's very, very good. On the other hand, if you're distributing a lot of profile 3, 4, 5 to mobile viewers, you may not see any bandwidth savings. You'll definitely see quality of experience improvements, but you won't see bandwidth savings, because instead of sending a 3 megabit per second X.264 stream, you're sending a 3 megabit per second LCEVC screen that's going to be higher quality, but you're not going to save any bandwidth. So again, all the numbers that I talked about before are BD rate stats, and in order to use those to estimate your real savings, you've got to translate those into real encoding ladders and then apply your distribution patterns, which rungs of your ladders are being retrieved. Otherwise, the numbers will have very little correlation with what your actual savings will be. And when I work with a consulting client to decide whether and how to implement a new codec, this is the first thing we do. You know, what's your encoding ladder? What's your distribution pattern? Let's compute the real world potential benefit of these new codecs. All the numbers I showed you a minute ago were not that. And this is, you know, if you want to see how we did it, you can download the LCEVC handout here. So question one is, you know, and these are tests that I've done after the article that we did in streaming media. So, you know, how effective is LCEVC with AV1 as a base layer? Now, when I first tested LCEVC with H.264 as a base layer, specifically X.264, it was 42% more efficient than X.264 on a BD rate basis, not the encoding ladder, not the distribution pattern. Encoding speed was about 2.5x faster, and the decode was slightly more efficient than H.264. And then we looked at it in these tests, in the tests I did for this article, against X.265 as a base layer, and we found that LCEVC was 22% more efficient than X.265, again, BD rate. And we also found that the encoding speed is 3.3x faster, and it was real-time playback with the same CPU usage or lower. So, you know, LCEVC with X.265 as a base layer played back as efficiently or more so than HEVC as a complete encoded file. So the question was, you know, what kind of benefit do you get if you encode LCEVC with AV1 as a base layer? So let's have a look. The procedure was I tested 4 of the 5 files that I tested for the article. The AV1 script was the same as in the article, and here's the LCEVC with AV1 as a base layer script. And here's CrowdRun. CrowdRun is a terribly hard file to produce, and in this case, the BD rate benefit for LCEVC with AV1 as a base layer was 0.57, not all that great. On the other hand, with Euro Truck Simulator 2, it was 15.75, and with Football Clip, it was 12.63. With Electra, which is the movie clip that we tested, it's around 20%. So that was pretty impressive. So it's 12.4% more efficient than AV1 standalone if you combine the results for all 5 files, or all 4 files that I looked at. The encoding speed was 4x faster, so you get a tremendous benefit in terms of encoding time as compared to AV1 as a standalone codec. And playback was more efficient than AV1 on standalone. So what I did here on the right is I played back the AV1 only file for 60 seconds, and this is the CPU utilization on the computer I use for all these tests, and I'll show you what that looks like in a moment. And then I played back an LCEVC file with AV1 as a base layer, and we see much less CPU utilization and much lower CPU utilization spikes. So you're going to get 12% more efficiency on the encoding side. You're going to save a ton of money on the encode. It's going to be 4x faster, and you're going to have more efficient playback, not less efficient playback. So it really is a green codec, even with AV1. So the benefit continues, even though it's a lesser percentage than what we saw with H.264 and HEVC. The second question I had was, how much benefit would you get with the MainConcept codec using 2-pass encoding? So in the story, we did, CRF-based encoding, which was 1 pass, very similar to live or single-pass encoding. The question was, would we see the same benefits in 2-pass encoding? So what I did here was I tested with full-length 2-minute files of the that I carved some of the test clips out of, except for CrowdRun, which is a 15-second file only. And then I encoded using the MainConcept preset that matched X.264 very slow, the X.265 very slow, as closely as it could. So that was the preset was 28. And then I measured both VMAF and low frame VMAF. And low frame VMAF measures the likelihood of experiencing transient quality problems in the encoded file. And let's look at the results. We're not going to look at all of them, just a couple of them. So CrowdRun, again, is very tough. We saw a BD rate benefit. And this, again, is 2-pass MainConcept as compared to 2-pass X.265, both HEVC codecs. So in terms of the overall BD rate, we saw a 2.64% advantage for the MainConcept codec. But for the low frame VMAF, again, the likelihood of experiencing transient frames, we saw a BD rate benefit of 10.64%. in the football clip, we saw a BD rate overall of 6.23 improvement, and we saw a low frame VMAF improvement of 14.78. And then again, Electra, which is our movie clip, we saw a 15.8% benefit BD rate, and then a 22.38% benefit in terms of low frame score. So very substantial for that movie clip. Overall, for all 5 files, it was a 4.34% BD rate advantage. The low frame boost was 8.71 BD rate. So the results are solid, not quite what we saw on the one pass, but that's why you have to test using parameters as close to the ultimate publishing parameters that you're going to use to make sure that the benefits accrue to the same level. And again, MainConcept, their specialty, their forte seems to be 4K content. You see the results from an MSU evaluation there. Hopefully we'll be adding 4K content the next time we look at these codecs for streaming media. So now we're going to look at the Codec USP, unique selling proposition, got it right for this slide. And why we look at that? Because the quality improvements may be not enough to trigger adoption. Sometimes you have to look at some of the other codec unique selling features. And then we'll look at HEVC, proven HDR capabilities, VVC with AR, VR and related features, and then LCEVC, which is a green codec, which is also playable in software. So checking time here, the proven USP, unique selling proposition or superpower for HEVC is proven HDR. And HDR is obviously key to distributing premium content. There's a much bigger perceived benefit with HDR than there is for 4K as compared to 1080p. So, and I should point out that there's a lot of noise about HDR and a lot of noise about codecs supporting HDR, but the only codec you can get for 10-bit HDR Dolby Vision today is HEVC. And all the advanced codecs can support 10-bit or higher for HDR, and all are working towards HDR 10 plus and Dolby Vision compatibility. And you see the draft spec for AV1 here, but most premium content publishers won't distribute a codec using HDR unless it's proven all the way through from the encoding side to the playback side. And I should point out that when Netflix started distributing video to smart TVs, which was their November 2021 announcement, they did it without HDR support. So if you look at the article shown on the right, another exciting direction we're taking is exploring AV1 with HDR. And again, Netflix is a founding member of the Alliance for Open Media. They're obviously very supportive of AV1. I'm not sure any other independent publisher would use AV1 until it supports HDR, particularly for HDR compatible content. VVC, the unique selling proposition is VR and AR and 360 features. And it's interesting that Apple is a VVC patent owner, and they recently bought up more patents. And the patent attorney I spoke to about that thought that they may be buying those patents because they relate to AR, VR, and particularly their Apple Glasses application. So if those markets, if that market becomes real this time, we were talking about 3D 3 or 4 years ago, and it never seemed to come to fruition. The current direction seems a lot more reasonable. But if it does happen, you're going to need some pretty serious compression. The Apple Glasses have 12 video cameras and 12 players. You need pretty serious compression to feed that, and I think VVC has a good chance of becoming that compression technology. And then LCEVC, the unique selling proposition is it's very lightweight on the encoding side. A lot of people are concerned about power consumption on the encoding for codecs. We'll look at that in a moment. And LCEVC is always going to be more efficient than the base layer codec, and we saw that a moment ago with AV1. And it's also it's also more efficient on the playback side. So it is a software codec as opposed to a hardware codec, and we'll look at that distinction more in a few moments. So now let's look at the known royalty costs, and obviously knowing what the cost is going to be is almost as important as what that cost is. And HEVC, I think we're in a good place. Nobody liked the pool structure, but I think as we'll look at in a moment, it really didn't hurt implementation, at least on the device and smart TV side. I think it did hurt publishing usage, but HEVC is everywhere that premium content plays. VP9, there's one patent pool. It's from Sysvel, that's disputed by Google. AV1, same deal. There's a Sysvel patent pool disputed by the Alliance for Open Media. I think the uncertainty in the marketplace that those disputes create are hindering the adoption of those two codecs. VVC, we'll look at those two pools in a moment. The structure of those pools are, there's the royalty on the encoder decoder, there's a per unit royalty, and then there's an annual cap. Now, LCEVC, we'll look at their royalty structure in a moment. They have a content royalty that the publisher pays. And the theory there is, while the publisher is getting the benefit of the reduced bandwidth cost and or the improved quality of experience, they should be the ones paying the royalty. And because the implementers, the player side and the encoder side don't have to pay the royalty, maybe they'll deploy LCEVC much more quickly. That's the theory. We'll cover it more in a second. And then EVC, the EVC patent holders promised to have a royalty structure in place within 2 years after the first draft international specification, which occurred, I think, in May 2020, and they're going to wait until the last possible minute. So nothing is out yet from them, which I think is holding back implementation of the codec, which to this point has been very, very minor. We'll look at that in a moment as well. There's, the known royalty cost for VVC. There's two pools, Access Advance on the left, MPEG LA on the right. What's unique about the Access Advance pool is that there's something called the multi-codec bridging agreement. So if you sign licenses for both VVC and HEVC with Access Advance, you get a significant savings of around 45%. Now we see there's a different royalty, a lower royalty for VVC with the MPEG LA pool for VVC free software. Access Advance has talked about coming up with a structure for lower cost distribution to browser support or other free applications. They haven't done anything with it yet, or I haven't seen any implementations of that, but I just wanted to point out that Access Advance has talked about doing something similar to what MPEG LA actually did. And you can read more details about the two royalty structures in the article that I've cited below. And then LCEVC, again, I think the royalty structure that they chose to distribute was one that was very friendly to the companies who were going to have to implement the encode and the decode. So the royalty is on the publisher. It's a different rate depending on the type of publisher that you are, but the annual cap is going to be 3.7 million. So if you're Netflix, you want to distribute LCEVC everywhere, or your Facebook or your Amazon, it costs you $3.7 million a year. And the ecosystem is free, and that really gives the publisher the ability to decide, okay, I want to use this, and I'll just pay the royalty. And then everything, they just have to use a software player that's compatible with LCEVC, like TheoPlayer and some other players. Now, if you tried to do that with VVC, you'd have to pay the $8 million royalty to MPEG LA, and then you'd have to negotiate some kind of deal with Access Advance. So, because you're going to have to pay the royalty on all of the decodes that are going to be out there. So I think VNova came up with a very implementer-friendly royalty approach that really does tax the company that's getting the benefit and makes it easier for any company who's not in the Alliance for Open Media to implement the decode side. And then rich parents, in codec deployment as in life, rich parents can open a lot of doors and accelerate success. So with HEVC, this is the famous picture of how messy the royalty structure was with 3 patent pools and a lot of companies who weren't in any of the patent pools. But all of these companies, or many of these companies, are major players in consumer electronics, chips, and other similar markets. And that led to pretty much ubiquitous implementation in smart TVs, a lot of phones, a lot of tablets, and a lot of dongles. So, the royalty structure was a mess, but having a lot of companies that had stakes in HEVC's success really did supercharge the implementation. And VP9, the major company who's implemented VP9 is YouTube. That's one parent, Google, but it's a pretty good parent. I mean, almost all of the smart TV implementations that we're seeing with VP9 was done because of YouTube, and specifically YouTube's policy of not supporting 4K videos beyond 1080p with H.264 and using always VP9 and sometimes AV1. And if we have time, we'll look at what that looks like. So this alone, this 4K video in VT9 format is what convinced Apple to finally support VP9 in 2020. Rich parents, the Alliance for Open Media is kind of the poster child for that. You've got control over desktop OSs, mobile OSs. They control the browsers. They control components. They dominate the content marketplace and other viewing platforms, and then they control infrastructure adoption. And we've seen this, in a ton of different areas. We've seen massive hardware support, massive software support in the browsers, and we've seen massive content support, which is kind of, that's what primes the pump. And that's, the primary, that plus the Alliance for Open Media not adopting some technologies, or members of the Alliance for Open Media not adopting HEVC specifically in their browsers, has really held back other competitive technologies. But AV1 is not the only technology with a lot of rich parents. And if we look at VVC, there's a ton of huge stakeholders, not so much that we're seeing from the Alliance for Open Media, but a lot in China and Korea that are equally important in those markets. And we see ByteDance, which distributes the TikTok application, and a couple of other applications from companies that are, very, very huge in those markets. And what I've done on the right is I took, most of the big rich parents, and this is from an iPlytics article. Sorry, I didn't show the source for that. But this shows what markets they're in and what where they fit into the ecosystem. And you see there's a lot of chip vendors, there's a lot of product manufacturers, whether it's consumer electronics or others, there's streaming publishers, there's infrastructure providers, and then there's technology providers. So, the point about this is I think VVC in many ways is probably not as strong as the Alliance for Open Media, but there's a lot of major companies who have huge financial stakes in VVC's success. Not so much EVC. EVC has, three main parents. They're very big parents and they're very rich, but all three are major VVC patent owners. So it's kind of confusing which one they would promote. EVC has made tremendous progress. That was one of the key findings of the article and all the quality studies that we've done, some of the encoding time studies, but there's not a lot of work on the implementation side. And frankly, there's not a lot of work on the VVC implementation side either, which was probably the most disappointing fact point that I kind of picked up on when I was doing research for this article or this presentation. And then there's LCEVC, which has VNova and a couple of investors in VNova that are industry players, but not huge industry players. And I just want to, VNova has other investors that are just not known in the industry. I think VNova has done a fabulous job, developing the codec, getting MPEG approval, proving the value proposition, and achieving ecosystem support. But compared to the other codecs with rich parents, they're pushing a rock up a hill. They've got a much more difficult task. And I think we have to realize that, a codec's success is going to be tied to how hard it is to succeed. Having, not a lot of supporters with financial stakes in its success, I think makes it a lot harder for LCEVC than it does for certainly VVC and probably EVC as well. And, AV1 is in a totally different category. Okay, so, those are kind of abstract factors to success. Let's look at, producibility and playability. Can you affordably produce the codec and software? That was one of the big things that held back AV1. And, what about live? Because live is obviously a key market, both on the origination side and on the delivery side. So again, in order to use a codec, encoding must be accessible. When I first tested AV1, this is back in I think 2019. Encoding time was 45,000 times real time. It's improved a bit since then, and a lot of the concerns we've seen with VVC, specifically, a David Ronca post in LinkedIn that talked about increasing complexity and how awful it was getting, and he used this slide to show how efficiency was kind of narrowing, was kind of reaching, non-incremental benefits, but complexity was getting very, very much more advanced. So what did I see? This is encoding time versus X.265. Here's the platform I use for all encoding and all playback tests. And again, this is compared to X.265. So VP9 was the fastest, and VP9 was 10x more efficient than AV1. We'll see why that's important in a moment. So, and again, we're looking at codecs and presets, and go back to the article to determine which codec I used and why I used the preset that I did. And really, I used the preset that I thought most producers would tend to use. But if you're using X.265 using the medium preset or X.264 using the medium preset, then these numbers don't really apply to what you're doing. On the other hand, LCEVC with X.265 as the base layer. Excuse me 1 second. LCEVC with X.265 as the base layer was about 0.3x the encoding time of X.265. So in addition to the 22% quality advantage, you get 1/3 of the encoding time. EVC baseline was 0.4x. The MainConcept using the 30 preset was 0.83. libaom was 1.02 times X.265 very slow preset. So it's pretty much the same encoding time. And that's from the 45,000 figure that we saw a moment ago to almost the same as very slow. Very impressive performance boost from the Alliance for Open Media crowd. VVC, the Fraunhofer implementation using the preset that I used was only 2x more complex on the software side than X.265 using the very slow preset. And that's, the 45,000 number was first generation AV1. This is the second time I've looked at VVC, and it's pretty much ready for implementation now from a quality and encoding time perspective. Very, very impressive. And then ditto for EVC main. This was an open source implementation. The codec itself is very, very new, and we saw 8x the encoding time, again, very far away from the 45,000 figure that we saw for AV1 during the first implementation. So I think a lot of the complexity fears are not being realized, certainly not by VVC, and it doesn't look like by EVC as well. So pretty impressive on that front. What about hardware? AV1, we saw the first live encoding hardware announced in, towards the end of, actually, I think this is April 2021, but I think it recently shipped. And I think we saw a bunch of companies, Vision ULR and Cisco making announcements about AV1 for WebRTC. I'll be testing WebRTC for a session at Streaming Media East, which hopefully will be live in Boston. I'm excited about getting out of this basement. I also think in 2022, 2023, you can expect a drop in cloud pricing for AV1 because the encoding times have gone way down. No longer can you justify 50x cost for AV1 as compared to H.264 or 8x HEVC because the encoding times have dropped. I also think companies like Xilinx now, AMD, are going to be announcing low-cost hardware accelerators that are kind of like the Google Argos video compression unit. I think VCU is what they called it, which is hardware acceleration for VOD encoding, not just live. So I think the entire cost structure for AV1 encoding is going to drop pretty significantly between now and mid 2013. We saw ATEM announce the first live VVC encoder. Not sure. Excuse me. That was 2020. I think that's more on the technology demonstration side, not a shipping product. If it is shipping, I apologize, but I don't know who you're sending streams to. And LCEVC has done a good job getting infrastructure support, ecosystem support on the encoding side, as well as the playback side. We'll look at that in a moment. So in terms of encoding hardware, I think it's going to be available for, HEVC, it's been available, it's pretty ubiquitous. We'll look at that in a second. In EVC, I've seen nothing announced. So HEVC is clearly going to be your best option along with H.264. I don't think VP9 is ever going to make it big in the live. You know, Twitch is using it with a Xilinx FPGA that's not available for public consumption. Not sure why they did that, but that's the only company I'm aware of that's doing VP9 live. You know, I think you'll see that subsumed by AV1 live encoding, you know, pretty soon. I think AV1, you'll see significant headway in WebRTC in 2022, 2023, and I think you'll start to see some live video as well. I think VVC, is going to be hindered by the playback side more than the production side, but I'm sure you'll see a lot of loud trials, meaning, you know, highly touted events that really don't amount to real-world implementations until 2023, 2024 timeframe. I think LCEVC is deployable anytime. It's already being deployed in some live applications, certainly contribution. I think it's really, you know, for VVC, you're waiting for technology to catch up. LCEVC, the technology is available today. It's just somebody choosing to implement it. And then EVC baseline and EVC main, no activity whatsoever in terms of live transcoding. The open source software encoder was wonderful. They did a great job with it, but it's not gonna produce live streams anytime soon. And then to deploy a codec, it needs to be able to play. So performance-wise, software only is best because then you don't need hardware. Hardware takes time to implement, costs money. And then compatibility-wise, support in the browser or operating system is best. It's the easiest way to do it, but there are workarounds, and we'll talk about what that might look like, for VNova and LCEVC in a moment. So 3 primary markets today for playback. You know, you've got your computers or notebooks, you've got mobile, and then you've got living room. And, you know, what's required for success in each market, you know, for computers and notebooks, you need hardware acceleration or software only playback, and it either needs to play in the browser or you have to have a pretty effective browser workaround. Talk about that in a moment. Mobile hardware acceleration is more preferred because of the battery life and the low power nature of those devices. You either need browser-based playback. For browser-based playback, you need direct codec support or you need a workaround. For an app, you can use any codec, but there are licensing limitations if you use HEVC or another royalty-bearing codec. And then for smart TVs or living rooms, you know, for OTT dongles, you pretty much need hardware support, except for LCEVC, which has been software upgradable on some set-top boxes. That's the primary use for, I think, Sky Italy. So where can the codec play and which require hardware acceleration? So these are playback tests on the same computer that I tested the encode on, and H.264 played back at 642 frames per second. VP9 was 621. HEVC was 388. AV1 was 357. LCEVC with X265 as the base layer was around 147, but VNova gates playback speed to preserve battery life. So I don't think that's an implementation of software versus hardware. And I think the first codecs that I mentioned, these 5, can play back in software on most devices. On the other hand, VVC was at 39, EVC baseline was at 59, and then EVC main was at 18. So I would call these hardware required codecs, although some of the rich parents of VVC have pretty impressive results in software trials. So this is Kwai, and they showed massive frame rates on Android devices, and you can see a link to this study here. And then performance on the iPhone 13 by ByteDance, this is the TikTok application, they also showed, you know, hundreds of frames per second. So again, normally with, you know, I've never seen a codec succeed in software only on the mobile side. We see a little bit of that with AV1, but certainly HEVC, nobody sends HEVC to a mobile device unless it's got hardware support, even though the playback times were very efficient, as we saw on the last slide. So I think, you know, as with AV1, stakeholders in VVC are going to push the envelope with software only decoding on the mobile side. And this, you know, to the extent that that works, that's going to accelerate hardware adoption on those platforms. But I think most traditional publishers who aren't, you know, who don't have a stake in VVC's success will wait until there's hardware support to supply it. So that's the playability side. Now it's the compatibility side. And, you know, if we look at browser support, and this is a website called Can I Use? You just go to Can I Use, type in the codec, and it tells you what percentage of browsers and OSs support it. And what we see for HEVC, which has been around since 2013, we're at 20%. Whereas for VP9, it's 97%. Of course, H.264 is 99%. AV1 has been around only for, since 2018, 2020 shipping version, and that's already at 74% because of Android, Chrome, Mozilla Firefox, and similar browsers. Just, massive support from Alliance for Open Media members, not named Apple. So what's the point? Browser-based playback, I think, a tremendous amount of web-based publishers who are not into premium content are playing back in the browser. ESPN, CNN, all news, all sports. 85% of Netflix viewers are watching on smart TVs. So if you're selling premium content, I think smart TV is the primary viewing station. But 99% of websites that distribute video care about browser-based playback, and the MPEG-based codecs are never going to get there. The only exception is LCEVC, because I think it has a workaround because of the royalty issue that we talked about a moment ago. And let's look at that. If you want to use LCEVC, you can find a compatible encoder. You can choose a compatible player, any of these, and then you basically contact VNova and negotiate a license, and the max is going to be 3.7 million. Now, you could do the same with VVC, but the maximums, right now it's 8 million for MPEG LA and 30 million for Access Advanced. So, because LCEVC is royalty bearing on the publisher, you have much more flexibility to implement it if you decide to implement it. And you can read more about that in this article listed here. I wanted to, show you what YouTube is doing with multiple codec implementations. I'm going to go through this really quickly because it's in obviously it's in the handout, but they're using AV1 only for videos with huge view counts, about 5.5 million and above, and VP9 for multiple thousand view counts. The number there was around 3,500, and all the way down, as we see here, to we see some, this is games, we see some AV1, but we see a lot of VP9. Late Night with Seth Meyers, pretty successful show, something that I don't watch as much as I used to, but 1.5, 2.5, pretty consistent over 7-figure view counts, and they're using VP9. And, for Dan Patrick, another show I look at a lot, these are, multi-thousand, they're all VP9. So VP9, I think with the Argos VCU, it got so affordable to start producing VP9 that YouTube just really started using it a lot more because it's cheap to encode and a lot more efficient than H.264. And then H.264 for anybody under the 3,500 threshold. And that was both me and a lot of the streaming media presentations. Kind of summarizing what I found. And the 4K story was a little bit interesting. Here we see that this is Top Gun 2 trailer. This is, dozens of millions of views. And we see that we've got AVC on the left up to 1080p. Then we've got VP9 all the way down to 4K, AV1 all the way down to 4K. And on the right, we see that, the AV1 stops at 1080p. That's why Apple decided to support VP9, because they wanted to get 4K videos from YouTube. And then here are the savings that we see. VP9 versus AVC was around 33%, and this is just based on the sizes of the files that I downloaded from YouTube. AV1 as compared to VP9 at 4K is around 28.36% more efficient, which is pretty impressive. And same in AV1 as compared to AVC, for 1080p, we're seeing 47% gains. So this is the whole discussion. No, let me not go there. Anyway, it looks like YouTube is, if YouTube can't afford AV1, I don't think you can afford AV1, but I think, again, we're going to see hardware out there like the Argos VCU that does AV1 encoding that's going to make that a lot less expensive. And I think, next time we come around with an updated Argos chip and we look at this, we'll see a lot more AV1 usage. So, let's look at the typical hardware deployment cycle, and this is for both mobile and smart TVs. The spec is finalized. Typically, the chip vendors start development then. Chips become available at the end of year one. Consumer products start developing when chips are available, and they come out at the end of year two. And then you need a critical mass of installed base, which takes a while. I'm saying 2 years here, probably closer to 3 years. So basically, it's a 4-year cycle from first draft international spec to when the products are going to be deployed in sufficient numbers to be addressable for publishers. Now, let's look at chip support, because that starts, that kind of starts the cycle. All of the codecs that we're talking about have already passed first draft international spec, and we see that HEVC is fully supported. VP9's got a ton of hardware support, and this is on the mobile side. AV1 has a ton of hardware support on the mobile side. I'm not really big on these manufacturers. I may have put some TV vendors here and some mobile computer vendors on the TV side that you'll see in a few minutes, but you get the point. There's a ton of support here, ton of support here, and there were no VVC, no chip support for what I thought were going to be mobile devices or computers. And that, again, was the most shocking finding in the research I did for this presentation, because this starts the cycle and we see nothing on the computer side. And at the same time, we see Qualcomm, I guess last week, decided to support AV1 in the latest rev of their Snapdragon chipset and not VVC. So that's a pretty big endorsement for AV1 and a pretty big disappointment for VVC. What do we see on mobile deployments for VP9? Apple added support in August 2020. That was because of the YouTube issue we talked about a moment ago, and it's been supported in Android forever. And Netflix famously started developing and distributing VP9 videos for download to Android devices in 2016. What about HEVC? Alliance for Open Media founding member Apple has full support of HEVC in hardware and software. And this is, the 20% we saw for browser support for Can I Use was all Apple. So even though Apple's a founding member, they're not drinking the Kool-Aid apparently. Most US or European phones and tablets have HEVC hardware installed. The Google OS, the operating system, has anemic HEV software support. It's only 960 by 540, but typically most of the high-end devices are going to support HEVC and hardware. What publishers do is they distribute video on apps. The apps query the device and say, hey, what level HEVC can you play? And typically they'll play hardware and they will send HEVC to those devices. So I think for most premium content distributors, you're sending HEVC to these mobile devices, whether it's Google, Android, or iOS. And then obviously if you're YouTube, you're sending VP9 to both. AV1 mobile deployments, again, Alliance for Open Media founding member Apple doesn't support AV1 in hardware or software. Android has supported it forever. The 4-year cycle I talked about a moment ago was supposed to bring mobile chip decode to the Android and even the Apple ecosystem by 2022. And this is from a presentation by John Porterfield interviewing David Ronca. And they said the chip shortages have pushed back deployments of AV1 hardware on mobile devices to 2026. And you can see the reference there. I think AV1 is lightweight enough to play in software, but obviously if you're a publisher, you're always going to be concerned about battery life. What about mobile deployments of VVC, LCEVC, and EVC? VVC, again, I think the stakeholders may try to do software only, but I don't think any non-affiliated publisher is going to try that. They're going to wait until hardware is supported in the devices they're targeting. LCEVC, I think, could be implemented in mobile devices tomorrow. It's just a question of a publisher making the decision to do so. And EVC, in terms of hardware support, doesn't seem to be on the radar screen. In terms of smart TVs, we see pretty good support for VP9 in smart TVs and AV1 in smart TVs, but these are, 4K without HDR support. And then we see some VVC support, but this is, 2 manufacturers out of many manufacturers. Again, it's relatively disappointing. So in terms of AV1, we saw the first shipping smart, here's the cycle. It started in 418, ships in 419. The first TVs were out at in May of 2020, right on time. Netflix launched to smart TVs 11/21, right around here, just before the 4-year mark. I think they're about 12 months behind. I think most non-AOM publishers are going to wait until HDR is available before they start encoding in AV1 as compared to HEVC or in addition to HEVC. VVC, same time frame. MediaTek, the first chipset came out pretty much on time. We saw prototype TVs at CES, so it's a little bit ahead of schedule. But I think the whole lack of chip support is really going to slow VVC deployment. I'm thinking, mid 2025 or beyond. And then I'm not seeing anything on the EVC side, so you can't even start the clock on them. So this kind of summarizes my thoughts on when these codecs will be usable, the software only versus hardware. Up here, browser, I don't see any of the MPEG codecs succeeding in the browser. Browser workaround, we talked about that. I think LCEVC has produced a good ecosystem workaround. We'll see if anybody takes them up on that. In terms of mobile hardware, HEVC and VP9 is available now. I'm a little bit more optimistic than David Ronca. I'm thinking 2024, but he probably knows better. Again, I think AV1 is lightweight enough to start playing in software now if you want to add that capability. VVC, I think, is 2025 plus. LCEVC doesn't require hardware, so I think that's a non-applicable. You can do it today. And then EVC is just not on the radar for any of this. Mobile software, I think for AV1 we've talked about. VVC, I think stakeholders only. LCEVC, I think, again, you can do that today. And then smart TV, STB support, ubiquitous for HEVC, VP9. Again, no HDR capabilities or no dynamic metadata HDR. AV1, I think we're going to wait until, I think most traditional publishers will wait until mid-2023 to start supporting those platforms. VVC, optimistically, mid-2024, but I really think it could be later. And LCEVC, again, that could be a totally software-only solution. Some third-party predictions. These are numbers from Bitmovin. And, which codecs do you plan to support in 2022? This is the Bitmovin Video Developer Report. You can get a copy of it here. And we see pretty good, these are the new codecs you're going to implement. We see pretty good support for AV1 and pretty good support for VVC. Now, this includes a lot of infrastructure and ecosystem providers. So, I don't think publishers will be using it at this point. I think it's more encoding vendors, cloud encoding vendors, player vendors, CDNs, those type of companies. I don't see any VVC implementation over the next 12 months beyond some trials. And this is Rethink TV. They're bullish on AV1 and VVC, but also HEVC and on the continued longevity of H.264. So this is H.264, this kind of arc on top, and we see it's still greater than 50% of the video through 2027, 2028. And hard to disagree. My predictions for 2025, I think AO Media is gonna become the predominant codec in the computer and mobile space. I think AO Media is just too much headwind for MPEG-based codecs. I think you'll see some LCEVC in those markets, but certainly not as much as you'll see H.264 continuing in AV1. And I think AV1 is going to subsume any momentum that VV9 had, but we'll see on that. Smart TV, I think, will be the last traditional holdout for VVC or MPEG-based codecs. Why? Because it's the traditional broadcast market and because of the whole HDR market. And I have the two big markets that kind of get me excited or, looking forward. The new ones are going to be the the AR/VR. We talked about why I think VVC has a pretty good chance to succeed in those markets, primarily the early feature advantage and just the focus. And I also think, you know, video encoding for machines is going to be a huge market, and that just strikes me as the type of collaborative standard that MPEG just does a really, really good job at, and the Alliance for Open Media companies probably don't have that much interest in. So these are kind of what I see as the markets and the codecs that will succeed in those markets going forward.